Okay, so welcome to the second wrap lecture. This one will be on RF oscillators, as well as the common collector amplifier. So last week we discussed the common emitter amplifier, and we'll see another type this time around. All right, so we have a lot of stuff to cover today. Hopefully it won't take 2 hours like last time. Let me get the pointer thing out here. Does anybody have any questions before we start? So first we'll talk about the assignment 1. So I think almost everyone completed assignment 1. And so I'll just kind of go over some points about it that some people didn't get and some people did. So here is a solution to that assignment. And I'm not saying it's the only one because there's technically an infinite number. But so what I have here is I have a 1.5 kilo ohm resistor in the emitter and a 1 kilo ohm resistor in the collector. And you get the 1K in the collector because we assume that the collector current was 1 milliamp and gain is minus GMRC. And at 1 milliamp, GM is roughly 40 millisiemens. So you need a 1K here to get the gain to be 40, or minus 40 rather. In the emitter, we have a 1.5 kilo ohm resistor in order to achieve the 2.5 volts from collector to emitter. And with the 1.5 kilo ohm resistor here and a 1 milliamp current going through it, that puts a 1.5 volt voltage at the emitter. And remember, the base is 0.6 volts above the emitter. So that puts the base at 2.1 volts. And this voltage divider here divides the 5 volt voltage source down to 2.1 volts. And that's how this circuit is biased and how we get the appropriate gain. Now, the actual gain you get is a little less than minus 40, or I guess the magnitude is a little less than 40, around like 37 or so. And there's multiple factors contributing to that. One is something called the early effect, which I did not talk about at all. And it's not that important for this project. So you can ignore it as far as we're concerned. Let's see. And there's other factors such as the nonlinearity of the transistor. There's something called the Miller effect, and that basically sticks a capacitance, a large capacitance, between the collector and the base, and that reduces your gain as you go higher and higher in frequency. And we can take a look at that later. And the other big thing was the input and output resistance. So on the input side, where we put a voltage at the base and measure the current going through it, take the ratio, people are getting somewhere between like 1.5 kilo ohms or 1 kilo ohm or 2.5 kilo ohms. I never actually mentioned how to calculate the input resistance, so I'll do that right now. So here I have R in is R1 in parallel with R2 in parallel with R pi. And I just realized that these resistors are not labeled R1 and R2. But let me correct that here. So for some reason, when I'm recording, my cursor likes to disappear and I have no idea where it goes. So I'll just there it is. So I'm calling this guy R2 and this guy is R1. Okay, so now things make sense. Okay, so now what we have is these two resistors in parallel with R pi, which again is the resistance looking into the base of this transistor. Let me write that again. So there's an effective resistance between the base and the emitter, and that resistance is R pi. And remember, because the emitter is grounded at AC because of this C3 capacitor, the effective AC resistance looking into the base of the transistor is just R pi. So you have these 3 resistors in parallel, and that gets you Rin. And so R pi, remember, R pi was equal to beta over GM. And at 1 milliamp collector current, this is roughly equal to 2.5 kiloohms. And we can't do anything about that. That's just what it is. And so we'll see, usually we want to maximize the input resistance of the amplifier. And so this 2.5 kiloohms is the kind of the limiting factor of the input resistance. We can't go any higher than this. I'm sorry, we can't go any higher than 2.5 kiloohms because where everything else is in parallel with 2.5 kiloohms, so you can only go lower. So what we'd want to do when we're choosing R1 and R2 is choose them such that they don't lower the overall Rin by too much, which is to say we want R1 and R2 to be much larger than 2.5 kiloohms. So that's kind of what I did here, where I chose 17.4 and 13.2 kiloohms, which are like, maybe 5 times or so bigger than the 2.5 kiloohms. So that brings up the input resistance a little. Now for the output resistance, which is just RC, that's easy enough. So here I have a 1.03 kilo ohm resistor for RC. And I should expect the output resistance to be something very close to 1 kilo ohm, which people found was the case. The reason why it gets a little smaller than 1 kilo ohm is due to the early effect, which I said we're not going to talk about much. And it doesn't have that big of an effect, so we can pretty much ignore it. So does anybody have any questions about assignment 1 or anything prior, or should we just move on? Okay, silence. We'll move on then. So if you've taken 115A, this should be apparent to you, but maybe not otherwise. So here I'm just modeling a generic amplifier using my great PowerPoint skills. So basically what at least a voltage amplifier is doing is you have some input voltage source, and that voltage source may have an internal source resistance. I'm calling that RS. So you can kind of think of this here as one separate block. You can't change RS. And the amplifier has some input resistance. I'm calling that Rin. And there's an internal voltage source to the amplifier. Remember, this is just a model. It's not how things actually are. But I have an internal voltage source to the amplifier, and that voltage is equal to the gain of the amplifier, AV, times VA, which is the voltage at the internal resistance. And then the amplifier has an output resistance, and that is connected to a load, which is what we want the output of the amplifier to drive. So there's 2 things kind of happening here. On the input side, we have a voltage divider between RS and Rin. And the voltage at VA is what really matters in terms of amplification. So we want to maximize VA with respect to Vin, which is to say, like, if we feed in 1 volt here at the input, like a 1 volt sinusoid, we want VA to be as close to 1 volt as possible, and that'll maximize the amount of voltage we get on the output. And so remember your voltage divider equation. If you don't, I recommend you do remember it because it comes up every day. Right, so we said Rn over Rs plus Rn. So if we make Rn very large, then you can see we can, in the denominator, we have Rn plus Rs. We can approximate that with Rin. And so this becomes Rn over Rn, which is 1. And so VA is approximately Vn, right? So that's nice and that's good. On the output, we have the same exact thing. We have a voltage divider between AVVA, between Rout and RL. So we have Vout is equal to AV VA times the RL, the voltage divider. And you can see if, oops, that's not what I wanted. Let's see. Okay, so you can see if RL is very small, then Vout just kind of goes to 0. That's not great. But usually we can't do anything about RL. It is what it is. So what we can do is something about Rout. And if we make Rout very small, we have the same condition as the input where Vout is essentially equal to AVVA. So basically, to summarize this, we want to make Rn large, Rout small, and that'll maximize the gain of our amplifiers. And so there's kind of a contradictory thing here. So remember with the common emitter amplifier, we had AV, which is the gain, was equal to minus GM RC. So we see that the gain depends on RC, but also remember that Rout is equal to RC. So by increasing RC, we increase the gain. But by increasing RC, we also increase Rout, which decreases the gain. So there's kind of a problem here where if we want to have a small RL, then we can't have a large RC and thus a large gain, because that'll create some voltage divider effect, which will reduce the gain. So basically, the problem here is that the common emitter amplifier has a large output impedance, RC, and it can't drive low impedance loads. Like if RL was, say, 50 ohms and RC was 500 ohms, then your voltage divider would be 50 over 550, which is something, reducing your gain by roughly like 9 or so, or 10, whatever the math is. And that's just going to ruin your day. So how do we get around that? Well, we use a different type of amplifier as the answer. So here's the common collector amplifier for those who haven't taken 115A. And it's the topology is kind of similar to the common emitter amplifier. So I just copy and pasted the circuit we had from the last lecture on the common emitter amplifier, except I removed the output on the collector and moved it to the emitter. That's the only thing I changed. And so that's basically what's happening. Instead of taking the output from the collector and having a resistor converting the collector current into voltage, we're taking the output from the emitter instead, and there's no shunt capacitor across RE anymore. So what effect does that have? Well, remember that with this RE resistor, VE, the emitter voltage, kind of follows VB. So if we move VB up in voltage, VE also follows. There's like a 0.6 voltage drop between them. So let me give some examples. So if VB is, say, 1 volt, VE is going to be 0.4 volts, or roughly there. If VB is 1.5 volts, VE is going to be 0.9 volts or so. Right? So in effect, if we ignore the 0.6 volt offset, VE is just going to be the same thing as VB. So if we take the output there, we're seeing a gain of 1. You might ask, what's the point if you have a gain of 1? Didn't we want a high gain? No, a low gain, and 1 is pretty low. You might as well just feed your signal straight through and bypass the amplifier if you're not amplifying it. And the answer lies inside the input and output impedances of this amplifier. Okay, so remember that the output impedance of the common emitter amplifier, the one we saw last week or 2 weeks ago, was RC. Well, take a look at it now with this amplifier. We have RE in parallel with this mess here. And I said there's an RS here. RS is the source resistance of the input voltage source, which may be 0, depends on the circumstances. But let's plug in some numbers here. So if we have a 1 milliamp collector current, that corresponds to R pi, which is 2.5 kilo ohms, if you recall. And let's say RS is 0 just for simplicity. So this term just goes away. So we have R pi over beta plus 1, that's 2.5 kilo ohms over roughly 100. So it's kind of around 25. And RE is 500. So we have 500 in parallel with 25. And because 25 is so much smaller than 500, this is approximately equal to 25. Right, because small resistance in parallel with large resistance gives you small resistance. So we've taken our output resistance in that was before like 1 kilo ohm or hundreds of ohms or even larger, and we've reduced it down to 25. So that's a big improvement. That means if we have a low impedance load, like if RL was 50 ohms or something smaller, we'd be able to drive it without losing much voltage across that voltage divider effect. If RL is 25 ohms in particular, we see a gain of 0.5 instead of 1, right? So just to make sure people are following, suppose RL was 75 ohms and R out is 25 ohms. What would be the effective, and assume AV is 1, so the gain from base to emitter is 1. Or sorry, ignore that. So if we go back here and we assume this AV was 1, what would be the gain in this case, the overall gain, including the voltage divider effects? Anyone?
Is it like 3/4?
Yeah, exactly. So if we assume the gain from VB to, I mean, this is not quite how it works, but if we assume the transistor has a gain of 1, and we have a 70 or 25 ohm output resistance, then the V out is going to be divided by 75 over 75 plus 25, which is 1 or 3/4, like you said. Okay, so let me clean this up here. Okay, so again, that's not quite how it works, but the actual gain is given by this. And this, if you use this equation, it takes into account that voltage division effect. So let's take a look at this equation here. Remember that R pi over beta plus 1 was 25 or so. And then we have RE in parallel with RL. So RE is the emitter resistor, this guy, and RL is what we're trying to send our voltage to, which is this guy. So that might be an antenna or something, or another amplifier, depends. So let's say RE in parallel with RL is much larger than 25. So we're driving a load that's much greater than 25 essentially. Then you could ignore this 25 ohm term, the R pi over beta plus 1, and this turns into 1. So the gain was 1. Which means if your load is large, a large resistance, then the gain of this amplifier is pretty much 1. But as you go lower, as the load resistance gets lower and lower, the gain starts to drop. And that's due to this R pi over beta plus 1 term being more important. But in general, your gain is going to be roughly, 0.5 or so to 1. So that might sound like it's bad, like your gain is less than 1, but we'll rectify that shortly. The other thing to notice about this is that the gain is positive, not negative. So with the common emitter amplifier, the gain was negative. Here the gain is positive, and that will come into play shortly. And the reason that is because, remember, if you increase VB, that's going to increase VE, and VE is the output. So a positive change in VB is going to cause a positive change in VE, which indicates a gain of 1. Okay, now for the input resistance, this looks like a complicated expression, but it's really not. So remember before with the common emitter amplifier, we had R1 in parallel with R2 in parallel with R pi. So the only thing I've added here is this beta plus 1 times RE. This should really be RE in parallel with RL. I'll fix that. So what effect does this have? So remember, last time R pi was kind of our limiting factor because we can make R1 and R2 big. R pi in this case was 2.5 kiloohms. And now we've added a beta plus 1 times RE in parallel with RL. And RE in parallel with RL, it really depends on the situation, but let's say it's somewhere like around 50 ohms or 100 ohms or something like that. And then we're multiplying it by 100. So 100 ohms times 100 is 10 kiloohms plus the 2.5 kiloohms. So now we're at 12.5 kiloohms for this term here. And before with the common emitter amplifier, that was 2.5 kiloohms. So we've added another 10 kiloohms to our input resistance, and so that's a good thing. So to summarize this, we have a large input resistance, we have a small output resistance, and so that this type of amplifier is good as a voltage buffer, which is to say if we have a large source resistance and a small load resistance, we could stick this common emitter amplifier, common collector amplifier in between, and it'll help drive that small load from a large source resistance. So the problem, of course, is that the gain is still small. So how do we rectify that? Well, it's pretty simple. We just stick a common collector amplifier after a common emitter amplifier. So if I draw that out here, simply a simple common emitter amplifier, where this is RC. And we have the biasing resistors and our input source here. Okay. Now we can feed this to a common collector amplifier. And then we can drive our load from that. So this guy here would be RL. And so I apologize for the messiness of this figure here. Let me just fix a couple things. So I should also add in the coupling capacitors. Oops. Okay. Hopefully that makes sense to people. So basically what I have here is this section is a common emitter amplifier, and that allows me to get high gain. But the problem with the common emitter amplifier is that it has a high output resistance. So I follow that up with a common collector amplifier, which doesn't provide me any gain, but it lowers the output resistance. And that allows me to drive a smaller load resistance. So does anybody have any questions about common collector amplifier? Otherwise, we'll move on. Okay. Nobody? Well, now we get to test your knowledge. So, I kind of put up this arbitrary example here. So this is the exact same circuit as before. Oh, I forgot to, let's skip this one for now. I didn't prepare this slide correctly, so we can get back to it in the assignment. So now we get to oscillators, the fun stuff. And we'll be using that common collector amplifier as part of an oscillator. So don't forget about the material I just talked about. So how do we use the oscillators in RF systems? Of course, what they do is they oscillate at a certain frequency, and one frequency only usually. And so the goal really is to create a stable frequency with a stable amplitude that doesn't start drifting off to other frequencies. And where are these oscillators used? Well, mainly in up converters, down converters, and mixers. So if you remember from the first lecture, usually in a wireless system, we need to take high frequencies and convert them to low frequencies, or take low frequencies and convert them to high frequencies. And those are accomplished through up converters and down converters. And so this on the right is kind of a high level system view of a mixer, or a up converter and down converter. So this block here in the center is called a mixer. What it does is it multiplies the two input signals. And the output, remember, if we have a input sinusoid and another input sinusoid, when we take the product, can somebody say what the output would be?
It's going to be like a modulate. It'll be a sinusoid where the amplitude is modulated according to the input.
Yeah. So if I say this guy is omega 1 in frequency, and this guy is omega 2, what you said is correct, but there's a little more to it. So the output would be something like cosine of omega 1 t times cosine omega 2 t, assuming they're in phase. They don't necessarily have to be in phase. And so this would be, a simple case of amplitude modulation, like he said. But remember, amplitude modulation, if you use your trig identities, you get your sum and difference frequencies. So you get a cosine of frequency omega 1 plus omega 2, and omega 1 minus omega 2. And if we were up converting, we could filter out this guy, and we're left with something of higher frequency. And if we're down converting to a lower frequency, we can filter out this guy, and we're left with the lower frequency, assuming omega 1 is greater than omega 2. Right? So usually we call the higher frequency, if we're down converting, we call the higher frequency the RF input, the lower frequency the IF input, and we have a local oscillator for LO, and that's just what's controlling what frequency you're down converting to. IF, by the way, stands for intermediate frequency, RF for radio frequency, but not a big deal. So if we have like a variable frequency local oscillator, what we can do is we can kind of move the IF up and down in frequency. And that process is called heterodyning, but we'll talk about that again later. Right now, we're just talking about the oscillator. So this would be for mixers. There's also frequency synthesis, which is just kind of a similar idea. You just want to generate a single tone, a single frequency, and do something with it. You might use it for testing certain components, like amplifiers or filters or something like that. But yeah, that's in general. It also might be part of a phase lock loop or PLL. We won't really talk about PLLs here, but they're widely used in communications. But they're just a term to remember maybe. So you might hear a bunch of different terms that refer to different types of oscillators. So I listed a few here. One is local oscillator, and that's what this guy is. It's just an oscillator that's driving a mixer to multiply two sources together. To multiply the RF by some frequency. You might have a voltage controlled oscillator, or VCO, which is just an oscillator where you can vary the output frequency by changing a voltage. There's variable frequency oscillator, which is just a type. It's exactly the same thing as VCO. There's crystal oscillators, and I have a nice picture of a crystal here, which you've probably seen before. The reason crystal oscillators are special is because the crystals they use tend to have what's called a very high quality factor, and we'll talk about that again. So keep that in mind. So basically that allows it to get a very highly stable oscillator, stable in frequency. And then there's temperature compensated crystal oscillators, which are crystal oscillators, and they stick the crystal inside an oven that keeps the temperature keeps the crystal at a very fixed temperature, and that keeps the frequency even more stable. And so there's other terms. We won't really be using crystal oscillators here, but virtually every electronic device has some form of the crystal oscillator. Like for example, in a microcontroller, you often have an external crystal that sets the clock rate for the processor. So what are we using an oscillator for? Well, we don't have a 27 megahertz function generator, which is just a device that outputs 27 megahertz. And we're going to be transmitting at 27 megahertz. So we want to be able to test our devices, should we build them in Spring at least, with the 27 megahertz signal we're going to be sending through them. And we don't have the right equipment for that, so we can make our own. And that's what an oscillator was basically designed to do, to spit out a signal frequency. And then the other reason is because we're going to be doing up conversion and down conversion, like I mentioned earlier, and we're going to need oscillators for that. Not necessarily at 27 megahertz, but other frequencies. Okay. So I stuck in this slide because I just kind of found it interesting. Most of you, or I imagine many of you, have worked with the 555 timer at some point, and you've created, perfectly nice square waves at certain frequencies with the 555 timer. So you might ask, why can't we use such a device as an oscillator for this project? And there's kind of a couple reasons. So this is just a small excerpt from the one particular 555 timer datasheet, and it specifies the rise time of the output and the fall time of the output as 100 nanoseconds. So, I mean, that means if you have a square wave that looks like this time here is 100 nanoseconds. So what's the problem with that? Well, if you take the reciprocal of 100 nanoseconds to get the corresponding frequency, what is that? That's 10 megahertz or so. And we're going to be oscillating at 27 megahertz roughly. So you can kind of sense a problem here where what's going to happen is that your square wave won't actually reach the flat point. It'll kind of look like this. And as you get higher and higher in frequency, that flat point will shrink more and more. And you won't even, like you'll barely get an oscillation or not even oscillate at all. Those weren't great pictures, but I hope you get the point. So generally, when you're trying to spit out a square wave, you need those rise times and fall times to be much smaller than the period of your frequency that you're operating at. And for these types of timers, that's not the case. So that's one problem. The other problem is output's a square wave, which I write here is rich in odd harmonics. So remember, if you take the Fourier transform of say Fourier series of a square wave, you get some energy at your fundamental frequency, and you get a bunch of other harmonics that are related to a sinc function and so on. And generally, we want a nice sine wave. Sometimes it's not that important whether you have a square wave or a sine wave, but in this particular case, we appreciate sine waves. So you need to have additional filtering on the output of the 555 timer to filter out those higher harmonics to leave you with the fundamental. The other reason is what's called phase noise or jitter. They're essentially the same thing. Digital people will call it jitter and analog people will call it phase noise. What that is that when your device is outputting some signal, it's not necessarily going to be at one frequency at all times. There's some noise in there that'll kind of jitter it back and forth between slightly different frequencies. So if you imagine a frequency plot, you'd want your oscillator to look like this, where this is in frequency. But what really happens is this kind of these tails in the spectrum that appear, and that's called phase noise. And that's very undesirable in wireless communications or communications in general, as well as for digital circuits. So it's not, isolated to just communications. And so you don't want that. It turns out with the 555 timer and those types of oscillators, you get high phase noise. And then the last point I wrote here is you can get ICs off the shelf that'll oscillate for you and have good phase noise and low harmonic levels, but that's no fun. So we'll continue on. We want to know how they work. So let's see how they work. So this is what I'm going to present is one particular viewpoint on how oscillators work, and it turns out there's multiple perspectives you can take that are all roughly equivalent. But this is kind of the most, or one of the intuitive ones that I've seen. So if you've taken 141, this will be familiar to you, but if not, I'll kind of review for you. So suppose you have this kind of system where you have an amplifier with a gain of A, and there's a feedback path from the output of the amplifier back to the input. And the gain of that feedback path is beta. So if you write out the transfer function from the output to the input, this should be over BF. I should correct that. It comes out to A, the gain of the amplifier, over 1 plus beta A. And this beta A term has an important name. I wrote it as A beta here, but it's called the loop gain, this guy here. And so what that represents is that if you imagine you have some signal here on the input, and then you follow it as you go into the amplifier, gets amplified by A, and then it goes through the feedback path, goes here, it gets amplified or multiplied by beta, and then it ends up back here. And you get some larger signal. Now the question is, what is the ratio of this larger signal, or smaller, it might be smaller, to the signal you started with? And that's what A beta is. So does that make sense to everyone? So now, of course, if you're feeding in a signal, it's going to go around in a loop again and again. And that will, so the output will not necessarily equal A beta. It'll be this A over 1 plus beta A. So, oops. So if you've taken 141, you remember you usually have some sort of input here, and you have the output. But in an oscillator, oscillators oscillate by themselves. There's no input to the oscillator. It just outputs some frequency. So we don't actually have an input to an oscillator. So let me get rid of that. What we want to do is have the oscillator oscillate by itself without any intervention. And so how do we accomplish that? Well, if you take a look at this gain equation here, and VF, the input voltage, is basically 0 because we're not inputting anything. So the question is, how can we have VO be some value when VF is 0? Anybody maybe think of something that would accomplish this? Oh, and it should be minus. Should it? Yeah, that should be minus. Anyone? No? Well, okay. Suppose beta times A is 1. Can anyone see what would happen?
And both sides would be 0.
Say that again?
Both sides would be 0 if BA equaled 1. I don't know what the significance of that is.
Well, they wouldn't be 0.
Or
Right?
divide by 0.
Right. So the significance of that is that we can essentially, basically this entire equation kind of breaks down, right? And the math kind of goes all wonky. But basically what that allows us to do is have VO be non-zero while VF is 0. So if you think about it more intuitively, suppose you have this input signal, or suppose you have some signal on the input, just for now, imagine that. And it gets multiplied by A. It goes around the feedback path, then it gets multiplied by B. And by the time it comes around, it'll be some sinusoid with some amplitude and some phase. And if the phase is equal to the input phase, then they'll add in phase. So they'll add constructively. And that'll kind of reinforce the input. It'll make the input bigger. And then when that signal goes around the loop again, and it adds up in phase, then it'll make the input even bigger. And you can see what's going to happen. The input's going to get bigger and bigger. The output is going to get bigger and bigger. And eventually, things are going to explode, right? It's an unstable circuit. So what if we made the gain, the loop gain, be a beta times A? What if we made that 1? such that when we go around in a loop, you're not really, you're not increasing the input, you're just keeping it as is, so that the input remains fixed amplitude. The output will remain a fixed amplitude because the output is just A times whatever is at the input to the amplifier. And if we make the phase of A times beta some multiple of 2 pi, then the output of the loop will be in phase with the input. So it'll add constructively. And so if we fulfill that criterion, then the input won't increase in amplitude, it won't decrease in amplitude, it'll just remain some fixed amplitude. And that is essentially an oscillation, a sustained oscillation, a stable sustained oscillation. And so this criterion is called the Barkhausen stability criterion, named after some guy, Barkhausen. So that's interesting in my opinion. So I know some of you haven't taken 141, so this might go over your head, but we can write A times beta in the S plane, which is to say we take the Laplace transform of those circuits and we can construct some sort of transfer function for that circuit. And so we'll get some rational function that's a function of the complex frequency S. And if you're not following this, don't worry. And for this system to be unstable, our poles need to be on the right half of the S plane, the poles being the roots of the denominator here. And if the poles are on the left half, the left half plane, then the system is stable and you won't oscillate. If it's unstable, then the output will just grow to infinity, and that's no good. So what we can do is place our poles somewhere near the j omega axis. And if they're on the j omega axis, then we oscillate. We don't increase amplitude or decrease amplitude. And we could have some sort of nonlinear circuit that kind of moves the pole to the left as the circuit starts increasing in amplitude. And then once the amplitude gets to a certain level, we can have the poles kind of move back. And once they're on the j omega axis, then we stop moving them. And that'll give us stable oscillation. So to those who have taken 141, hopefully that makes sense. What I'm trying to say is that in order to start the oscillation, we need A times beta, the loop gain, to be greater than 1 at the oscillation frequency of interest. And so that corresponds to an unstable circuit, which I wrote as scary here, because normally we don't like unstable systems. And once the oscillation starts, increasing in amplitude, then we can move the poles back to the j omega axis, and that'll correspond to the oscillation criterion, where A times beta is equal to 1 at the oscillation frequency. And if you're interested, I wrote this requires some nonlinear circuitry, and which means you need something more than a resistor, a capacitor, and an inductor, because those are all linear. And I wrote that's also scary because normally we don't like nonlinear effects in our systems. So if you didn't understand the slide, no worries. But it's interesting if you do. All right, so how do we actually construct such an oscillator? Well, there's tons of different ways. Some of you have taken digital systems classes like M16 or whatever they're called. And you might have seen something that looks like this. Where each of these is an inverter. So just a NOT gate essentially. And we take the output and wrap it all the way back to the input. And so if you imagine you have a like 1 volt here, and the output of this inverter will be 0 volts, let's say, or let me not use volts. Let me just say they're ones and zeros in binary. And this inverter will turn that into a 1, and this inverter will turn that into a 0. And there's a problem, because now we've connected a 0, which is the output of this guy here, to a 1, which is what we said the input was. Well, how do we overcome this? These inverters don't act in infinitely fast. So there's some propagation delay from the input of the inverter to the output. And so, say that's time tau. So we feed in a 1, it'll take tau seconds to get to 0, and so on. And by the time this becomes 0, that'll force the input here to be 0. So now this turns into a 0. And again, the 0 will propagate, turn this into a 1, turn this guy into a 0, and turn this guy into a 1. And it'll keep oscillating like that. So this is one form of an oscillator. And you can kind of guess what the frequency would be. It would be 1/3 tau, the frequency of oscillation. And can we apply that Barkhausen stability criterion or oscillation criterion to this circuit? And the answer is you can. You can think of the feedback path, beta, just being 1, because we're just taking the output and feeding it back to the input and not doing anything to it. So beta is just 1. And then the gain, well, we multiply by, if you think of these as like 1 to -1, or -1 instead of 0, you can think of these as having a gain of -1 and some phase, because there's a delay. A delay corresponds to a phase shift. And when these delays, which is to say phase shifts, add up to 360 degrees, then that would be your oscillation frequency. And sure enough, that's what it is. So that's...
Sorry, can you repeat that again?
Yeah, so well, let me clean up this figure here a little. I'll note that this is not really related to the project, but I just kind of find it interesting. So this guy will be -1, which gets turned into a 1. This guy starts at -1, gets turned into 1, and that gets -1. Sorry, this is +1. 1, it gets turned into -1. It gets turned into +1. And then, did I do this right? No, I was right the first time. Okay. That's -1, it's turned into 1. Okay. I messed up again. Okay, now it's right. So what I'm saying is beta is 1, and then A, which is the gain of, the amplifying path, this guy here, at the oscillation frequency is just equal to 1. And so it's really -1 times e to the j pi. which comes out to 1, right? So how do we get the J pi? The J pi comes about because of these delays here, the taus. When you add up all the delay together, and at the oscillation frequency, that delay corresponds to a phase shift of pi. Does that make sense?
Right. So we would choose these inverters in a way that the tau would be 1/3
1/3 of the period.
1/3 of the period for the oscillating frequency we want.
Yeah, exactly.
Got it.
And so, yeah, this type of oscillator is used all over digital, like CMOS circuits or integrated circuits. You don't see it that much for like communication circuits or wireless systems, and the reason that is because it kind of has a what's called a low quality factor, and that increases the phase noise of the oscillation, which again is like the jitter and the frequency. And so remember that I said phase noise is important for wireless systems, and so that's why this type of oscillator is not so great for communications. But it's just kind of interesting to see that the same analog calculations apply to both digital and analog circuits. So anyway, back to the LC oscillator, which is what we're actually going to be building. This diagram here shows what a particular type of oscillator called a Colpitts oscillator, which I think is one of the most simple oscillators, I'd say, but it's also widely used. So how does it work? Well, remember we need an amplifier, we need some feedback network, and that's what we have here. We have a common collector amplifier, which I described earlier in the lecture. So we have just a regular transistor biased by R1 and R2, and we have a emitter resistor, RE, and we're taking the output from the emitter. Now, we have a feedback network that's composed of an inductor and 2 capacitors. So we're taking the output that's at the emitter, and we're feeding it into the feedback network. And then that creates some voltage at this point, which creates some voltage at this point here. And we're feeding that back into the base of the transistor, which is the input to the common collector amplifier. Okay, so we calculated the gain of the common collector amplifier before, which is some value over some other value. But remember that it was positive and it was real, a real number, not a complex number. So so that means that the feedback network has to have a gain which may be greater than 1, might be less than 1, but it has to have a gain that is also real, because when you take the product, they have to multiply to 1, which is a real number. So the gain has to be real, and the magnitude of that gain has to be the reciprocal of the common collector gain. Does that make sense to people? Because you want it to add up to 1.
Shouldn't we want the gain for the feedback network to be complex and varying with frequency so that at a desired frequency it's real and 1/A?
Yeah. Let me clarify. So the in general, beta, the feedback network gain, is a complex number, and in almost every case, at the oscillation frequency, that complex number will turn into a real number, like you said. And so you only want this to occur at a single frequency. You don't want it to occur at multiple frequencies, because then you're just oscillating at whatever frequency, but not the one you want. Right? You only want one frequency in general.
All right. Okay. Got it.
Okay.
So
then,
we're kind of discussing this, assuming we're like talking about one frequency.
Yeah.
Got it.
Sorry, I should explicitly say that, but yes, I'm implying that. So yeah, if you ever seen, which I'm sure most of you have, just an LC tank circuit, just looks like this. You got L, you got C. The impedance of this network becomes infinity at a single frequency, right? And can somebody say what that frequency is?
Is it 1 over root LC?
Yeah, exactly. So a similar thing will happen here in this oscillator, where these capacitors will resonate with the inductor at a certain frequency. And maybe you can guess what that frequency will be. When it comes out to L times the series combination of C1 and C2, which is just C1 times C2 over C1 plus C2. And so it turns out that'll be the resonant frequency of this oscillator. We'll come back to that. But keep this in mind as we keep going. Now, I mentioned crystal oscillators earlier. What crystal oscillators do, they'll replace this LC network with just a crystal, a piezoelectric crystal. And it turns out that those crystals also have resonant frequencies. And when you buy a crystal, you'll buy one with a particular resonant frequency. That's due to the physical dimensions of that crystal. And it'll basically have the same effect, where at some particular frequency, that crystal will become infinite impedance or zero impedance, but it'll be real impedance, not complex. Okay, so let's first talk about the amplifier. We talked about the common collector amplifier earlier. Right, I kind of, this is kind of the same equation that we had before for the gain, except I kind of move things around and use different variables. But this is still equal to RE over RE plus R pi over GM. I'm sorry, R pi over beta plus 1. It's the same equation if you go through the numbers. Or I guess not numbers, but simplify things. So anyway, there's many ways to implement this amplifier. The common collector is just one particular way, and in my opinion, it happens to be the easier way, and it works well. So, in terms of how to bias this amplifier and which resistor values to choose, there's kind of some rules of thumb here. One is you want RE to be on the large side, and we'll see why that is. The other thing is you want R1 and R2 to be on the large side. And this again makes the input resistance of this amplifier larger than it would otherwise be. You don't want it to be too large, otherwise your base current will cause weird things to happen. But you want it to be on the large side. All right. Then you have the feedback network, which I said it resonates at this 1 over square root LCT, and LCT, sorry, CT is the series combination of those two capacitors. And if you want to find out how you get these figures, you can go through the math, and if you're interested, I can show you what kind of math you have to do. It gets kind of messy. But anyway, some things to watch out for when you buy an inductor off the shelf or you make an inductor. It's basically just a coil of wire, right? But those coils can get very long, or the wire itself can get very thin, and that'll cause the inductor to have some finite series resistance. So your equivalent model for the inductor, let me redraw that. Your equivalent model for the inductor will look like an inductor in series with a resistor. We'll call that resistance RS, or series resistance. And so that'll cause some loss in the feedback network. And so if you remember from your early circuits classes days, if you have a LC tank that has no loss, and we give it some, voltage here, initial voltage, and then let the circuit do its thing, that voltage will just start oscillating. And it'll have a constant amplitude, and it'll just oscillate to infinity. Now the problem with this is that our inductor has some loss, so there's really a resistor here. And that means instead of this, we'll have an oscillation that'll decay and eventually die out. So what we kind of hope to do here is use the amplifier to sustain that oscillation at one particular frequency, which is the frequency that this tank oscillates at. Okay, so we're compensating for the loss with the amplifier gain. The other thing is I haven't talked about quality factor yet. I'll talk about that at the end. But the more loss you have in this inductor, the lower this quantity called the quality factor, which I'll define later, the lower that becomes. And it turns out the lower your quality factor is, or which is to say the more loss you have, that'll further increase the oscillator's phase noise, which is undesirable. So, any questions?
So would it be right to think about this as basically us taking an oscillator tank and we keep topping it off with the amplifier to compensate for the slight loss because of the series resistance of the inductor?
Yes, that's exactly how you think about that. So what I presented earlier is kind of the feedback way of looking at oscillators. There's also something called the negative resistance approach. And so I can write this series RL model as a parallel I'll call it RP and LP. And I'm going to have some capacitance here too, right? Because we're resonating with the capacitance. And what we want to do is get rid of this resistance. So that's what the amplifier does. If you, let me write it down here. We have our common collector amplifier, right? And we're taking the output at the emitter. If we consider this like one port and this another port, and we wanted to know what's the effective resistance looking into here. It's not going to be Rn, because Rn is usually taken from the base to ground, not base to the emitter. So it's a little different than Rn. So I don't know, I'll call it Rn for lack of a better letter. And so what we want to do is make Rn equal to minus Rp, which again is this parallel resistance. So what we'll get in the end is you have your parallel resistance Rp, we have our inductor, we have our capacitor, and then we have that resistance Rn, which is equal to minus Rp. And Rp in parallel with minus Rp gets you infinite resistance. So you can kind of ignore these two resistors, and you're left with just your perfect lossless LC tank.
Okay.
So Yeah, so the goal here is to bias this amplifier such that Rn equals minus Rp. If Rn is less than minus Rp, which is to say you're kind of overcompensating for the loss, what'll happen is your oscillations will become unstable and the amplitude will keep growing, right? Because you're just going to keep adding more and more energy into the circuit.
Right.
So that's actually what you want, it turns out. The reason that is because as the amplitude of that oscillation gets bigger and bigger, it turns out that Rn will start dropping in magnitude. So the way the circuit works out is it starts off unstable and the oscillation amplitude will keep growing, which means that you're overcompensating. And then once the amplitude gets to a certain level, then the Rn will start decreasing in magnitude until it reaches exactly minus Rp. And at that point, you'll have a stable oscillation.
Got it. And in all of this, we're really only concerned with the frequency of the signal. We don't particularly care what amplitude it ends up at for that frequency, as long as it exceeds like our minimum like logic levels.
Uh, you do care about the
Like
amplitude. We'll go on.
do we particularly care about the final amplitude of the oscillator signal?
Well, when you use the oscillator in a system, you do care because, like, if you're driving a mixer with your oscillator, sometimes the mixer requires a certain amplitude level to function correctly. We'll talk about that. So you don't want your amplitude to be some random number, and you can control the amplitude, but the math actually is really hard to calculate what the amplitude will be. So I'm not going to talk about that here.
All right.
Yeah.
Yeah, thanks. That helped clear it up a bit, in my
Yeah.
mind at least.
Okay.
Yeah.
In order to increase the amplitude, though, what all you do is make the gain of this amplifier larger, right? That'll increase the amplitude. So yeah, hopefully that gives you some more insight. All right. So I went ahead and did the math for you, and it turns out that if you satisfy this condition, then your circuit will oscillate. Which is to say, when GM, the transconductance of the transistor, is exactly equal to this quantity on the right, then you'll exactly fulfill that Barkhausen criterion where the loop gain is exactly 1. But in order to get the circuit to start oscillating, you need it to start off unstable for the amplitude to increase. And so for that reason, we need GM to be greater than this quantity here. So there's some assumptions I made when you compute this. Oh, and I wrote here RS is the series resistance of the inductor. But the reason I don't mention the series resistance of the capacitor is because it's so much smaller than the inductor that you can just ignore it, really. So anyway, the assumptions here, R1 and R2 are large, which I said earlier. And we make RE on the larger side, and I'll say exactly how large. And when you make RE large, remember that makes the input resistance of the common collector amplifier larger. Because remember, we have that beta plus 1 times RE term in the input resistance. So that means Rn will be large. And the reason we want to do that is because we don't want to kind of load down the LC tank. Like if RE was small, for example, you would just have a resistor across this capacitor and that'll create even more loss. So we want that resistor to be large. And how large exactly? Well, at the oscillation frequency, C2 has some reactance, which is 1 over omega not the oscillation frequency times C2. So if we make RE a lot larger than this quantity here, then we're in business. So that's the what you want to do there. Oops. Okay. So that's one assumption. Everything else here. Yeah, so and then the last thing is just make sure R1 and R2 are large-ish. Exactly how large they need to be is not too important, as long as they're not small. You usually want them to be larger than the reactances of the L's and the C's, such that they don't affect that part of the circuit. Okay. So other things in general, when you're choosing components for RF systems, you have to make sure that your inductor and capacitor values make sense. And it's hard to tell what'll make sense and what doesn't make sense without experience building things like this. So I'll just kind of give you an example. When you're building, like, I don't know, power systems, or like working with DC voltages, or 555 timer, for example, you use capacitors in the microfarad range usually. And then for like decoupling microcontrollers, you might use like 10 nanofarad or 100 nanofarad capacitor. For RF systems, when you're working up in the megahertz or gigahertz range, capacitors are usually in the tens to hundreds to thousands of picofarads. So I'll say good range for capacitors is, at least for this type of project, is 10 picofarads to, I'll say like 10 nanofarads. If you go higher than 10 nanofarads, what will happen is that your capacitors won't work anymore at the frequency we're working at. And if you go below 10 picofarads, well, what will happen is that the stray inductance of your circuit, like the parasitics, will kind of, overpower the actual capacitor you put in your circuit, and everything's going to be off. Like you sneeze on it and your capacitance will change. So you don't want that. Now for the inductance, as you go higher and higher in inductance, again, they'll stop working at these frequencies. So I'd say a good rule of thumb, at least here, is, let's say 10, at least for cheap inductors. If you go really expensive, you can get better. But let's say 10 microhenries to, say roughly 100, or maybe I'll say 50 nanohenries. So that gives you a lot of range. For this particular oscillator, I'd recommend using something around 1 microhenry. But you can try different ones. And let's see, if you want, you can go on DigiKey and start punching in numbers for different inductors and capacitors. And specifically for inductors, you'll see this Q factor stuff a lot. And you want the highest Q factor possible, really. For like whenever you buy an inductor, you always want the highest Q factor. And it turns out that getting higher Q factors costs more. So I'd say for this project, you want to limit your Q factor to at most roughly, let's say 50 to 40 or so, because getting higher than that is pretty expensive. And lower than that will increase your phase noise, like I said, and make your oscillator harder to oscillate. Now, the last thing I have here is you don't want to make your bias current too high. And the reason that is, if you make your bias current too high, then your output amplitude gets too large. And that means instead of a nice sinusoidal looking thing, you get something that looks more like a square wave. And that also comes with more phase noise. I keep saying increased phase noise without explaining it much, but just go with me. If you go too low, then your circuit just won't oscillate, or it'll oscillate but with a very tiny amplitude. And that's, you don't really want a tiny amplitude. Okay, any comments? Okay, now we get into the quality factor. So I write here, described how much energy is reactively stored in a component versus how much is lost. And then I shove a bunch of equations at you. Well, it's not very intuitive, so I made a demo. So let's look at the demo. In LT Spice, of course, the finest circuit simulator out there. What did I call it? I called it Q factor. Okay, so I have here the world's simplest LC tank. You're all seeing this, right?
Yep.
Okay. So I have a perfect capacitor here. I have a perfect inductor here. And if I calculate the resonant frequency, let's see. Let me pull in a calculator. Where's my calculator? And the calculator's not appearing. Let me try that again. I have no idea where my calculator is, so believe me when I say that the resonant frequency of this is 1 megahertz. And I stick a 1 ohm resistor here. So at 1 megahertz, can someone say what the resistance is looking into this LC tank? Remember that parallel LCs become infinite resistance at their resonant frequency. So,
Just 1 ohm.
Yeah, exactly. We have infinite resistance in parallel with 1 ohm, and that gives you 1 ohm. So and I have a current source here, and let me open this here. I have a AC amplitude set here. So I'm just sweeping frequency and seeing how this circuit responds to basically a 1 amp current source. So I'll simulate and I'll plot the voltage. And let me increase the frequency range here to, I don't know, 100 kilohertz to 10 megahertz. Okay, and then we plotted the log scale. Great. So if you take a look at the voltage at exactly 1 megahertz, and let me change this to linear scale, you see that the voltage is basically 1 volt, which makes sense. We have one amp that's running through 1 ohm. Oops. Oh, I found my calculator. Anyway, Zoom is in the way, it turns out. Move Zoom. Okay, here we are. So yeah, at 1 megahertz, our voltage is 1 volt, which makes sense. So let's say I change this to 1 kilo ohm. Can somebody say what the voltage will be?
One kilovolt.
Yeah. This is definitely not a realistic scenario, but just go with it. All right, so it's kind of hard to tell, but when I get this cursor right in the right spot, let me zoom in a bit, we're getting something close to 1 kilovolt. We're not exactly on 1 megahertz, so it's not going to be exact. I can add more points to the simulation. Let me go like this. All right, so that'll give us more resolution. And yeah, we're basically getting 1 kilovolt. But you also notice something else that happens. Let me go back to 1 ohm. So notice how smooth, like the rise and fall of this voltage is. Like you can think of it as the bandwidth. The bandwidth of this, rise and fall is pretty large. But if I go back to linear scale here, you can see this voltage reaches the minus 3 dB point. Roughly, so that's 154 kilohertz. And on the other side, it is roughly 6.4 megahertz. So the bandwidth is roughly 6.5 megahertz. And so if you were to use this type of tank in an oscillator, you can see that that loop gain is going to be close to 1 over some range of frequencies. When it's exactly 1, that'll be our oscillation frequency. But when it's close to 1, that'll be where the circuit's like just barely oscillating. And so you can kind of think of that as it wanting to oscillate at those other frequencies, but it can't quite. And that's what that phase noise really is. It's kind of jittering between, a range of frequencies, and that's not what you want. So here I have a 1 ohm resistor in parallel with these guys. And that means that this LC tank is super lossy. Like we took our nice perfect inductor and capacitor and we shoved the 1 ohm resistor across them, which will basically suck away any energy that we excite into the circuit, which means that this tank, this LC tank, has a very low quality factor. Now, when I increase this 1 ohm resistor to 1 kilo ohm, see, now we have a nice spike at that 1 megahertz. And that corresponds to a much narrower bandwidth. And also, if we were to stick this into an oscillator, much less phase noise, because that loop gain is only 1 at a much narrower range of frequencies. So if I zoom in a little, we can get the bandwidth of this guy. It's roughly, what's that, around 80 kilohertz or so, or even less than that. It's more like 40 to 50 kilohertz. So we've gone from 6.5 megahertz to around 45 kilohertz. And if we increase this even more, which is to say increase our quality factor of this tank, let's say 100 kilo ohms, now it's even sharper. And of course, the amplitude is going to go up, but that's not too important here. So that's intuitively how to look at quality factor. Now, if I go back here, I have some equations here. And this is just showing how to calculate quality factor based on the LC tank. And you notice, like let's say we take the first equation. So we have an R, a resistor in parallel with an inductor. And it's just that resistance over the resonant frequency times the inductance. Well, you don't see a capacitor in there, right? You might wonder where that capacitor is in that equation. And that capacitor actually is inside the omega naught, the resonant frequency. Because remember, the resonant frequency is 1 over square root LC for LC tank. And so like this equation and this equation are exactly equivalent. Like if you replace omega naught with 1 over square root LC, plug that in, work out the math, it will come exactly into this equation. So you can use whichever one is easier, really. But for inductors, when a manufacturer sells you an inductor, they'll say there's some quality factor with that inductor. And you'd use this equation to calculate the effective series resistance of that inductor. So it's kind of like, you're kind of like ignoring, like assuming there's a capacitor there. What would that quality factor be, or that resistance be? So it's kind of iffy, but that's how you do it. So like I said, for an oscillator, we want high Q components, and that'll minimize the loss in our tanks. All right. So does that make sense, everyone? Okay. All right, now we get to the fun part, the second fun part. So let me give you a demo of a Colpitts oscillator here. I think this is the one. Yes. We're almost done here. So ignore this stuff on the left. Let's just focus on this guy. So what I did here is I, copied exactly the oscillator schematic that's in the PowerPoint slides. Like, it's exactly the same thing. And the only thing I added is, oops, on the output here, I'm just capacitively coupling the output to get rid of the DC part and feeding that into just a 100 kilo ohm resistor. And the reason I chose 100 kilo ohms again is because I don't want to load the circuit. I don't want to affect the circuit. So I just chose something arbitrarily large. All right. So I completely randomly chose these component values. So who knows what frequency it actually oscillates at? We can calculate, of course. So let's do that quickly. Let me pull up the calculator here. So can somebody say what I should do here to calculate the resonant frequency of this oscillator? Someone, please. Please. Did anybody follow the last hour and a half?
Okay. Well, we want 1 over for LC, so I know the L term is going to be 1 micro Henry in that term.
Right.
C, okay. Are we just taking the equivalent capacitance of C2 and C5, or I don't know how C1 plays into that? Is it just all 3 of them?
Right. So I guess I should mention what C1 is doing. So ignore C1 for now.
I imagine that's why that's why I was hesitant. I was like, I don't know what that's doing.
Yeah, I'll talk about that right after we do this. So continue.
We got C2 and C5.
And they're in series, right?
Yeah. So series capacitors are 0.1. So help me out here, David. Come on, man.
Well, you got 2 capacitors in series, which means the overall capacitance is smaller, right?
Yes.
So 0.1 in parallel to 0.1 nanofarads is 0.05.
Cool.
Okay, so
I'm not doing this mental math, man. You have the calculator.
I mean, you just divide by 2, but okay.
All right, thanks.
All right, so we're doing the inductance times the capacitance. Thank you for your participation, by the way. And we'll take the square root of that and take the reciprocal of that. And that's omega naught. Now to get the frequency, the standard frequency, we got to divide by 2 pi. So divide by 2, divide by pi. And I messed up because now we're getting something times 10 to the minus 9. So let me try that one more time. So you get 1 divided by, I took the reciprocal twice, I think. So 1 divided by this times 0.05 times this. So that will take the square root. We'll divide by 2, we'll divide by pi, we get 22.5 megahertz. That sounds better. So we should expect this circuit to oscillate at 22.5 megahertz. And I'll explain C1. So why is C1 there? If we didn't have C1 there, then what would the base voltage be at DC? Anyone take a guess?
2.5.
No, so that's the problem. If we did have the capacitor there, then yes, it would be 2.5. But if we got rid of this capacitor and just shorted from one side to the other, then we have an inductor that's connecting the base to ground. And remember that inductors are short circuits at DC.
Right.
So at DC, this base would be 0 volts. So yeah, so in order for this transistor to turn on, we need this capacitor there, and that allows us to DC bias and set the base voltage essentially to something non-zero. And I made this 1 microfarad. So it's basically the same thing as the coupling capacitors we had with the common emitter amplifier. All it's doing is acting as a short at AC frequencies and open at DC frequencies, or at DC, not frequencies.
If C1's purpose in life is to prevent a short circuit between the base and ground, why is it placed where it's at, between L1 and C2? Why can't it be shifted over?
I could do that. It can
okay,
be.
Okay. Does it not affect the LC tank at all?
Not at all.
Okay.
No difference. Assuming you make this big enough, the capacitance. It turns out that there's another type of oscillator that's related to the Colpitts oscillator called a clap oscillator. And what you do is you just make this capacitance a lot smaller, which makes it more significant at the oscillation frequency. And you can kind of control the resonant frequency by changing this capacitor, but here I'm not doing that. But anyway, so let me run the simulation here. So oops. Let's look at the parameters here. I'm starting at 0 seconds, and I'm running till 10 microseconds. So let's just see what that looks like. I'll plot the output voltage here. And sure enough, we only have a DC source, so there's no magical sinusoidal source that's creating this. We start at 0 volts on the output, and the oscillation just builds up until it reaches some level, and it stays there. And so if we zoom in a little, it looks roughly sinusoidal. It's not a perfect sinusoid, but it works. That's good. What's interesting is you can kind of notice there's like some overshoot here when the amplitude increases and then it settles down. It's just something interesting to notice. Oh, I should also mention the other thing I did is if I right-click the inductor, you can add a series resistance. So just to make this more realistic, I added a 4 ohm resistance to that inductor. But anyway. Okay, so question is, what frequency is this? And I mean, you could do it the hard way by going like this until you get enough resolution. And then you take a couple cursors. Oops. Take a couple cursors, place one at one peak, place the other one at the other peak. And then let me find where that little window went. Oh, here it is. The little window will tell you the frequency of that signal is 19.85 megahertz, which is not the 22.5 I said earlier, but we'll see why. So that's the hard way of doing it. Let me show you the easy way. Let me first what I'm going to do is take the Fourier transform of this, but I first need to cut out this beginning part because that'll affect the Fourier transform. I only want the sinusoidal portion. So let me change the simulation parameters. So instead of starting at 0, I'll start at, say, 2 microseconds. That's when the amplitude becomes stable. So I'll change that to 2u. And I'll probably increase the stop time to like 20 microseconds because that gets me more resolution or precision in the frequency domain. So I'll run that again, and we have still have our stable oscillation. If I zoom in, get the same thing. But now I'll right-click the waveform. I'll press View. I'll press FFT for Fast Fourier Transform. And it brings up this window with a bunch of stuff. All you need to do is press OK. And it'll bring up the Fourier transform of that signal. And as we should expect, we get one peak at a certain frequency. And then we get other peaks at harmonics at that frequency. And there's this weird thing here, but that's like almost 70 dB below or 60 dB below the peak here. So you can ignore that little ripple there. Not important. So let me zoom in to this peak here. If I put my cursor, or I can go like this, create a cursor, move that to the peak. And I'll bring back that window. And it tells me, again, it's 19.8 megahertz. Okay. So now you might ask, why is that 19.8 megahertz and not 22.5 like we calculated? And well, the reason is because this transistor is not perfect. The transistor itself is rated to work only up to 250 megahertz. But even below that maximum frequency, you get some non-ideal effects. And namely, what you get is capacitance between the base and emitter, the base and collector, and that'll add, specifically the capacitance between base and emitter, will add directly to C2 because it's in parallel. And so that'll shift your resonant frequency a little. So, there's two ways to go around this. One is you compensate for the bad transistor by changing your values here. The other way is to change your transistor to something better. So that's what I'll do. I brought in a transistor model in LT space, and I'll show you how to do this for the assignment, because we'll be using this transistor, the MMBTH10, which is the transistor designed for RF circuits. So I'll just right-click on the name of this transistor and find out where the window is over here. Okay, and I'll change this to MMBTH10. And now let me rerun this. We still get oscillation, and still looks roughly sinusoidal. And I'll do the same Fourier transform trick. And I'll zoom in here, plop down a cursor, and find out where that stupid window went. Oh, here it is. And right now it's 22.06 megahertz, not exactly 22.5. Then again, that's because of there's still some residual capacitance between base to emitter, and you can't really do much about that. But that's good enough in my book. And then I should also mention, if I close this, for this particular transistor, which is the one we'll be using in the assignment, if I measure between base to emitter, let me stop the oscillation first by getting rid of that capacitor. So now I just have DC. So from base to emitter, I have roughly 755 millivolts. Now remember before when I said base to emitter is usually 0.6 volts when the transistor is on. And while that's true for certain transistors, but not all transistors, for this particular one, the transistor turns on when base to emitter is roughly 750 to 800 millivolts. That's just the way it is for this particular transistor. Okay, so let me put the capacitor back, rerun this. The other thing I want to mention, notice how this still has a DC component, but notice how the amplitude of this goes from roughly like 820 to minus 90. So roughly, what is that, 910 millivolts peak to peak. So let's say roughly 450 millivolts amplitude. Remember that number. Now let me change the bias current. And I'll do that by increasing the base voltage slightly. All right, now we're going from roughly, let's say 0.1 minus 0.1 to a little over 0.9. So let's say roughly 1 volt peak to peak. So 500 millivolts amplitude. So by increasing the bias current of the transistor, we've increased the amplitude of oscillation. And so that's just something to keep in mind. The more gain the transistor has, which is to say the higher the bias current, the easier it is for the oscillations to occur and the higher the amplitude will be. If I decrease the amplitude significantly by decreasing the bias current, which I'll do by decreasing the voltage at the base, you'll see that now our oscillation is roughly 200 or 300 millivolts amplitude. And yeah, it follows the expectation. So I'll put that back. So any questions on this demo here? No? Okay. All right, we're almost to the end. I did not fulfill my desire of taking less than 2 hours, but oh well. So this assignment will be focusing on designing first a common collector amplifier and then second a oscillator based on the common collector amplifier theory and everything. So last time we used the 2N4401 transistor for the common emitter amplifier. This time we'll use the MMBTH10, which is an NPN transistor. Same thing as the other one, just different parameters. So for this amplifier, you'll assume a 50 ohm source resistance, which is the resistance of like the internal resistance of the voltage source on the input. And then you're driving a 50 ohm load. And then the goal here is to choose the collector current of the amplifier and everything such that the output impedance of the amplifier is 50 ohms. Which means that the total gain will be roughly 0.5. It'll be a little lower than 0.5, but it's about 0.5. And the reason why I'm choosing 50 ohms is because 50 ohms is like a kind of standard resistance in the RF and wireless communications world. If you keep going farther in the field, it'll come up a ton. And it turns out that the antennas we're using have a 50 ohm impedance at the frequencies we're operating at. So technically, you could use this common collector amplifier you designed to drive the antenna. Okay, then the second part is actually creating an oscillator. So for this particular oscillator, you want to choose a resonant frequency, an oscillation frequency of 28 megahertz. You might ask why 28 megahertz? And because that'll allow us to convert a 1 megahertz signal up to 27 megahertz, which is what we're transmitting at. and we'll see how that happens next week. And then lastly, what I recommend is you start with an inductor in the range of half a microhenry to a microhenry. What exactly it is, not too important. And then make sure your quality factor is less than or equal to 40. And given the quality factor, if I go back here, you can compute the effective series resistance using the second equation here. And then using that effective series resistance, you can determine what bias current you need for your oscillator. Okay, so any questions? I think that's all I have for today. I'll post, like I did last time, a document describing what exactly you need to do for the assignment. And I want to make this assignment due Friday of next week. Same thing as last time at 8 o'clock. And then we'll probably have a lecture next week on either Thursday or Wednesday again. The reason we didn't have a lecture last week is because I was too busy. So I kind of want to have these every week such that we don't have a whole week of nothing for this project. So any concerns or questions, comments, etc.?
Do you think that all the lectures are going to be 2 hours every single week, or do you think they'll shorten the like?
I really hope not.
Yeah, these is pretty long.
Yeah, I apologize, but I kind of want to cover the material I did, and the recordings are online, so if you get tired, you can always watch it later. I think so. Next week will be on mixers, right? And I don't have that much to talk about. Definitely not as much as this. So that one I can promise you will be shorter.
Thanks, David.
Yep. So no one else?
No questions for me. Not yet, anyways.
Oh, well, you know where to find me if you do.
Discord lab.
That's right. Monday and Friday in the morning. All right, so I'll stop this recording.